Okay, so today we'll study something for which we have kind of created background in the last class. Okay, and it's very important topic, and you will be doing an assignment on this one. Okay, so I have taken contents from primarily this CS161 University of California Berkeley course. Okay, and the contents also come from this classical paper. It's called Smashing the Stack for Fun and Profit. This paper by LF1, and he was a hacker. And while hacking, he found out, this interesting idea that the stack, runtime stack, can be the runtime stack has some issues, and those can be exploited. Okay, so I will suggest you to download the paper and try to go through it. Just have a look at it, and you should be able to understand it. Is most widely referred paper, okay, in this area of buffer overflow. So to start with, we'll start with preamble, and then we'll jump directly to buffer overflow problem. Okay. Okay, have you heard of this Morris worm? Okay, this is an interesting thing, right? It happened quite some time back, almost like 20 years back. So this worm was released. It's called Morris worm. It's named after Mr. Morris. Okay, Mr. Morris was graduate student at Cornell. Okay, it's a good school, one of the top, maybe in top 5 in US. And he was also son of NSA chief scientist. NSA basically, you would have heard of this organization in US, right? It's a security agency. All right. He's a big guy. Chief scientist is a really big guy there, right? So, and I'm sure he was very, very bright because studied in Cornell, and he was convicted under Computer Fraud and Abuse Act, sentenced for 3 years, and for 400 hours of community service. Okay, so he was very curious guy, and then he created this possibly for fun, a worm, and injected into system, and then it spread. Because see, note that when we use the word worm versus virus, okay, when we use virus in general, maybe biological virus as well, then a virus needs some carrier to carry it, right? So like the virus that we are facing nowadays, coronavirus, if you sit in a room and don't go out, nothing will happen to you. Okay, somebody has to come to you with the virus, right? And then that carrier will infect you. Same thing happens in computer virus. Computer virus come over something, right? Maybe you have used your flash drive or flash stick is infected with virus, and then you use it, then it transfers to your computer, or it can come over email. Wherein the worm has property that it moves by itself, it replicates by itself, and it does not require medium. The difference in virus and worm is that worm can use mechanism for its movement and replication. So basically replication can happen without any medium. Okay, so he just created this for fun and wanted to test it, and then it's gone out and then spread all over the world. And he claimed that he intended to do harmless. Basically, his intention was good, not causing harm to anybody. But it created new copies as fast as it could and overloaded the infected host. And Amount of damage was 10 to 100 million. Okay, obviously when your money, for example, you are running a company and virus infects your company, a worm infects your whole organization, you have to shut it down, or so you have a losses, right? And for you who has losses, it is a criminal activity, and you may not think that some nice person who's studying in Cornell has done this, right? So what? So that's the reason he was convicted, but now he is a professor at MIT. Possibly you can look at his LinkedIn profile and so on. Okay. uh, and why we are discussing this is because the worm's propagation technique was using buffer overflow attack. Okay, all right. So basically, I mean, we are not going to get into what he has done and so on, because we need to understand VEX system, and then we'll have to see what some feature that he has used, some function which is fingered function. And so it's basically by sending a special string to daemon, finger daemon, and worm cause it to execute code creating new worm copy. All right, so I will request you to please read more about it. Okay, so when you're developing a malware, even for fun, it can be dangerous, right? Okay, so when you're trying to learn hacking, which is ethical hacking, and you hack by mistake somebody's computer, even my computer, for example, or any computer in institute, then it's a criminal activity, right? So if you are doing criminal activity, then you can be punished. So best way, if you really want to try, is that take approval, that I want to hack your machine, could you please allow? So that's the best way, right? Okay, and you can get paid for that. Okay, many companies pay external agency to get into their systems. Okay, find holes in the whole security thing, and then by once they know what are the holes, then they can plug those holes, right? That's a very simple way of, a less expensive way of finding out the holes or vulnerabilities. Okay, so with this, let's start today's presentation. Okay, why are we studying this? Because this is still the most used vulnerability. Although most of the OS and new chipsets have taken care of this, but still you will find a lot of old servers running that have still these holes. Okay, this kind of vulnerabilities. Okay, so this is the diagram where you are, this scenario where you are in airport. Okay, what do? You just give your copy of ticket. If you have, in many countries like US, you just need to give your passport or some identity card. Okay, and then the person, based on that, person will find out more about you and then issue a boarding pass. Okay, so this is the process. Okay, so but in order to do that, you will have to fill up a form, right? Make a reservation. Okay, so you have filled up the form. This is basically form in US. Okay, any application, and it could be through any website, but internally, the interface could be slightly different, but finally same data will go to backend computers, right? And this is the way it goes. This is the form. Okay, wherein there are fields like name, first name, middle name, last name. Okay, date of birth, etc. Okay, gender and all that, right? Okay, so you'll have to fill up this form, and now this will, then based on that, backend will do some reservations, and then when you go to airport, it will look on the terminal something like something like this. Okay, so she has filled in her name as Alice Smith, and so on, right? So it will appear like this, that this is the name, and this is a class, coach class, which we call here as economy class. Okay, and any special instruction, none. So this will appear on the terminal of the officer, or the person who is doing check-in. All right. Is anything wrong? Do you see anything wrong in this one? Nothing. Okay, it's fine. Okay, now if she does the following, okay, first name she writes as it is, last name she writes Smith, then extended this HHHH, certain number of H's, right? Now this will system will accept it, because name could be anything. Okay, nobody stops you from putting so many H's again in your surname, right? And then it will appear something like this. Do you see any problem here? Any problem?
Class is changed.
Yeah, class is very good. Class is changed. Now you as a hacker, you want to take advantage of this vulnerability, and this may not be a crime actually. You are doing best from your side, and then if system is bad, what can you do? Okay, what can you do now? Now instead of HHHS, you put something so that this becomes, economy class to say coach class to say first class, or something like this, or business class, or something like that. Okay. So now if she writes something like this, Smith, and then certain number of spaces or blanks, and then write first, okay, then this it will come something like this here. Okay, note that this is just an example. Program logic could be have more checks, but this was actually a vulnerability in the past. Okay, so now what ticketing agent will do? Will give her a boarding pass with first class seats, right? All right. Okay, so now where is the problem? Problem is here, right? By inserting padding characters or spaces and exploiting the lack of boundaries between the lines, Alice now appears to be in the first class. It is fine, but Alice has to be smart enough to find out how many spaces to put. Okay, otherwise the first will not appear in the right place. Okay, so attacker can exploit lack of boundaries to control areas in memory which they are not supposed to control. All right. So now we can see how what's wrong with the ticketing system. Okay. So here the problem is that your name and your airline's class are stored in consecutive block of memory. And if you enter a really long name like Smith HHHH or whatever, the system doesn't check that your name is too long, and your name starts to overflow into memory space used to store your airline class. Okay, you can of course fix this, but when you are doing the, whoever has done the programming might not have thought about, anybody can exploit it. If the programmer think about these problems right in the beginning, because security is never in the mind of programmers, they never think. I mean, I have not seen in my career anybody thinks about security. They think always about efficiency, okay, and other factors. But if the security thing is kept in mind, then this problem can be avoided, right? All right. So now look at your favorite programming language, C. Now here you define an array, character array, name, this character array with size 4. Okay, 4 bytes. Okay, and now you store into 5th location, okay, name 5, some character A. Okay, now this thing, your when this thing goes to basically is created in stack. Okay, because this will be created, this is all temporary thing, is a variable, right? Okay, it will be created in a stack. Okay, runtime stack. Okay, that we have seen. I mean, this is runtime or memory image, and you have you basically text, whatever you have seen in the last class, right? Then you have heap, and then you have stack. And just for simplicity, let's assume that these. So in a stack, you will this variable will be stored. Okay, this and now of course there will be memory location adjacent to that. Okay, so now A will be written there, here in this location, right? Because 0, 1, 2, 3, and then you are using fifth element of this array, so it will come here. If you use 4th element, it would have come here, right? So now the question is that C in general does not check bounds. Why is that? See, this problem won't exist in say Python. So C is called memory unsafe language. Now the designer of C gave the power at the hands of programmers. They assumed that all programmers are bright, intelligent, and will not make mistakes. This is the power. Okay, it gave very less power to compiler, etc. Right? So these checks are not done. Okay, let's move it. So this code is technically valid, but doesn't check bounds, right? And hence there is a problem. So it's largely because C has no concept of array length. It just sees this as sequence of bytes. Now, if you allow an attacker to start writing at a location and don't define where they must stop, they can overwrite into other parts of the memory. So there's a learning. So attacker can use locations which access location and can write on locations which they're not supposed to. Okay, so let's look at the example and become clear. Okay, so this is a code, the C code. Okay, and we call it vulnerable code. Yeah, just a minute. Okay, all right. Okay, this is a function. Okay, and before that, before this function is called, you have array called name with length is 20. All right, and then you get in that function you run this gets name. You remember what is gets? Gets what will do? Anyone?
The input
You get a
and
string.
string.
Yeah, input is string, right? You can do it from keyboard. All right, so now let's see what will happen. So gets function will write bytes until input contains new line character. Okay, not when the end of array is reached. Essentially, if you are writing a name array, it's of size 20. You define this of size 20, and you get a string called name and then string, this function will check only this character, new line character. Till that time it will assume that that's the string. Okay, so string boundaries comes from new line character, so it will start filling this. It doesn't it's not bothered about whether it's 20 bytes or 25 bytes or 30 bytes. Until it gets back a new line character, it will continue to write, right? So all this location can be written if name has more than 20 bytes. Okay, so let's look at this way. Now this is fine, because there's, it's, even if you write something here and there may not be anything useful, it's okay. Now let's look at this example. Okay, so this is the same. There's a name is array of size 20, and there's another array which call instructions essentially of size 20, and then we assign this as value none. It means there is instruction which, if this value of maybe program logic is something like this, if this value of this is none, then do nothing. Okay, all right, now you run this gets name. So what will happen? So it's something like this. This is your stack. Okay, so a stack, these will be reserved for you. So 20 bytes, and this is one word of 4 bytes. It will start from here, it will go up to this point, 1 2 3 4 5, right? So 20 bytes, where each word is of 4 bytes. Okay, and then it will reserve, okay, it will reserve a space for 20 bytes for instruction. So this is space for 20 bytes. So right at this point in time, no values has been assigned, right? So it just stack, this space is created. All right, now control comes here, and this function call, or this statement is run. Okay, so it's a gets name. Okay, now writing starts from here, it goes upwards, and if name that you are entering through keyboard is very long, then can overwrite here. Okay, all right, so now we can see that this can be overwritten, and this can be exploited. Okay, by when program runs in next, or in the further execution of the program after this, and when the program logic checks, if the value is none, then do something, it finds something else. Okay, all right, so this is another example. Name array of 20. So in the stack, these 4 words will be reserved for name, and then there is an integer which you are defining as authenticated. This is authenticated, so it will be assigned value 0, and you read a string name. Okay, now you can make this instead of 0 as 1 by having something here in the name when you write, when you actually type. Okay, similarly, so basically instead of 0, if you can make it 1, because with 20 bytes of name, whatever it could be, say 20 bytes, let's say 1 up to 20. So these will be filled with some characters, say B, for example, B, or whatever, or maybe 2 times B, or whatever. You have to calculate, right? How much, what you have to do. B, 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 B. Each character, say, let's assume is 1 byte. So you do it. Okay. Okay. All right. And here you put 1. So a string could be, now note that it's a little endian, so you'll have to find out the sequence. What is the right sequence? It could be 1 b b b b b b, something like this, and then this will becomes 1. Okay, so now something that is not authenticated becomes authenticated. So this is, let's look at another vulnerability. Okay, just a minute. Sorry. Okay. Okay, here we have character array of size 512. Okay, so in a stack, this space is reserved, and then there is a character string which we define as which is named as command, which is of 12 bytes, the one here. Okay, all right, when you get Slime, you can do one thing, is that you intelligently put whatever command you want to execute here, which is malicious command, which is it's not supposed to. Okay, okay, and then you have a exec cv command. Now note that all these things is in a machine instruction. So program is running this, so hacker will not know what all this is, right? So it somehow assumes that it could be command there. Okay, and then because this thing may not, all these things are not known, all he gets is opportunity to type something, and if it types here some command, the command will come here, and then in the program, if there execv, I mean, you know what execv is, right? Because we have learned this in part of process, right? So this command will start running. It will essentially it will change the code of the process. It create a, and the process code will change, and then this command will start running as part of the main process. Because we have process, we fork it, then we run execv, right? Then fork process starts running that new code. Similarly, here you assume that it's not forking, it's not happening, execv directly you're running. So the code of the running process becomes a new code, which is that of a command. Okay, all right. Okay, what is it happening here? What is this thing? What is this? Anyone?
Function pointer.
Is a function pointer, right? We studied this in OS course, right? For others who have not studied function pointer, please study function pointer. Not many of us use this, this, what do you call that, feature of C, but it's a very interesting way of using it, right? Okay, so this is a function pointer, essentially a pointer to a function. Okay, so I mean, in otherwise, to when you call a function, actually implicitly compiler does the same thing, but here explicitly you define function pointer. Okay, so what's happening here then, when in the stack, first we have 20 bytes for name, and then 4 bytes for function pointer. Now when function pointer command comes, and this function, then actually control goes to somewhere, right, where this function points to. Is a pointer to a function, and function may be somewhere here, so it will start pointing to starting instruction, and then that can get executed. Okay, but this has to be written appropriately then, because all these things again is not seen by hacker. Okay, because there's a machine instruction. Now there is also possibility in when source code is known, because for example in Linux and many other for a lot of application source code is known, and this vulnerability is visible, then hacker will know that look, there is a vulnerability and this can be exploited. But in general, commercial software like whatever Microsoft and Google and many others develop, source code is not known. So now hacker has to think, try, but assume, attempt, and then try to find out vulnerabilities. Okay, any question up to this point? Note that we are talking only about stack, which is in the runtime image, right? When the when program we execute, it creates a stack. During execution of that program, that becomes process. Okay, so we're talking just about a single frame in the stack. Okay, so this all is stack. We are not talking about heap and so on. Okay, all right. So buffer unsafe languages are dangerous, which is C and C++. But they are very powerful, and that's the reason they are used heavily in in any system design. And also it has been used heavily in application side, but Python etc. are now changing it because of different reasons. C is also very efficient, does not require too much of space in comparison to many other languages, right? But now space is not really the constraint. Earlier when space was, when we had just 64K of memory, RAM memory, then all these things were very important, but not anymore. All right, now let's spend few minutes to look at what are the common weaknesses that has been found by a group. It's called CWE. You can go to this. This is a forum that finds out weaknesses, right? So you can go to this link and find out what are the topmost weaknesses in this year. Okay, all right. So here they list every all weaknesses, right? And I've subscribed to their email. So whenever they find a new weakness, not this one, but there's some other agency, government agency, US and in US, and they keep sending me email. Okay. So now this list has top 25 most dangerous software weaknesses. Okay. Okay. Most common and impactful issues experienced over previous 2 calendar years. So these weaknesses are dangerous because they are easy to find, exploit, and can allow adversaries to complete takeover system, steal data, and prevent the application from working. Okay, let's look at what are these. You double click on this, you'll get the one that's shown here. Okay, let's expand. Okay, so the rank number 1 is out of bound write. Something that we just studied, right? Okay. And then second heavily used weakness by hackers, of course, or cyber criminals, is improper neutralization of input during web page generation. It's called cross-site scripting. We'll study that. Then there is something called out of bound read. Earlier it was write, now read. Improper input validation. Okay, and so on. You can go through the list. Integer overflow is another Overflow we have studied in computer architecture course. What is overflow and how integer overflow can give malicious results, right? Wrong results. And this can also be exploited. Null pointer dereference, this is another issue, right? Many programmers don't know how to use pointers, how to initialize it and so on. Then hand coded credentials is kind of backdoor in my understanding, right? I mean, hand coded credentials is that I mean, the code you say that if user is X, then allow, and then X could be your name, right? If you're a developer and you create a code that if user process ID or user ID or owner of process is say your name, then allow following accesses, right? So this hard coding can be very dangerous because you think nobody will know this, but cyber criminals are smart enough to find such gaps out. Okay, missing authorization, incorrect default permissions, and so on. Okay, please go through this list, and this list keeps changing. But something that is interesting is that something that we are studying now is heavily exploited vulnerability, is still ranked 1, and this is known to everyone. Even Windows, the one Microsoft knows that this is a vulnerability, Linux knows this is a vulnerability, Intel knows this is a vulnerability, and they have also designed solution for that. But this again, the solutions are not 100% foolproof. Okay, all right, and there are old servers with where with old OS and so on, or old chipset where this vulnerability still exists. Okay, so let's come to more interesting part called stack smashing. So far we have seen that by overwriting we can create some problem in the system, right? Okay, but still we have not discussed how we can take control of the system. Okay, so now let's look at stack smashing. Again, this comes from the same paper which we referred in the beginning. All right, so this is most common kind of buffer overflow problem, and it occurs in stack memory. That's the word stack we use. Okay, so now we have studied stack in the last class. That's the reason we spent 1 full hour to understand the concept. So what are the values in the stack that an attacker can overflow, and attacker will like? Attacker may not just want to crash your system. It may, but that's not really a smart thing, right? Crashing a system is pretty simple for a hacker. Okay, but more than that, taking control of system is bigger challenge. So what is the value that we studied is most exploited? Yesterday we discussed this. Anyone?
Changing program counter.
Yeah, so basically what we save in stack is variables. Okay, various variables come, then we have arrays, we have struct. Okay, then apart from that, two important things is that when we make a function call, then we store previous functions, which has our caller functions. Two things, right? First is the starting frame starting address. Okay, and where it should program count, when the new function that's in execution, when it's complete, where the control should go back. Okay, or the program counter, which we call it instruction pointer in Intel terminology, right? So these are the things we save: local variables, function arguments, then where the frame of the caller function is starting. So this is a caller function. Okay, and this is, note that this is also in stack, right? And so there is a stack frame. So now when this caller function, in the caller function, starting address of the frame is given by frame pointer, and then stack is at the top. Stack pointer, oh sorry, stack pointer is at the top. And apart from that, in the text segment, there is a counter called program counter, or we call it instruction pointer. In Intel, both are same, and we'll say which instruction we are going to execute next. Okay, so now something that's, so when this calls a function, then another stack frame is created. Let's assume it's created here. Okay, and when the execution of this is over, then again next instruction will be executed, from where it stopped. So something that's really important is program counter or instruction pointer of caller function, which was saved in the stack. Now if we can override this, right, to different address, then next instruction that will be executed after the calling function is over will be something that hacker wants. Okay, so now before that we'll use little bit of Python syntax to illustrate our concepts. So don't worry about it, we're not going to compile it and so on, but you know this, right? Some of these, right? When this the ABC plus DEF becomes bigger string called ABCDEF, and then when A is multiplied, A star 5 becomes 5 times A in the string. There's concatenation and so on. So there are many things you would have studied, so we'll use some of these, not much, but just for you, because once you get this notation you shouldn't get confused. Okay, so let's look at this code. Okay, this is a C code. Okay, char name 20 and then just gets name. So this is for name up to this, and before that you'll see that instruction pointer, old program counter on instruction pointer is stored. That's for the caller. The caller is calling this, right? Caller is calling this. So once the execution of this is over, it will go to caller next instruction. So all right, and so it's like this. Okay, so get will start writing from here. Okay, and now attacker wants to execute instruction of address dead beef. Okay, so basically there is some address dead beef. Okay, let's assume it's here or somewhere. Okay, and then it wants to execute that. So what will do, it will start putting values here and put dead beef here. Okay, so it's like this. It will put all whatever junk characters like AAA. Okay, and then SPF also it puts AAA. Okay, and then here it puts dead beef. If you is a little endian, so you can see DE AD BEEF here, right? And then termination, this is for termination, because it's the what do you call the new line character or whatever. Okay, so now so the input is this one, and it is overwritten over both return instruction pointer or return or saved program counter, and then frame pointer. Okay, and when execution of this is over, control goes back. Okay, then basically the old program counter is popped out, and next instruction to be executed is something that's in the popped out program counter value, right? Okay, all right, so this way code can malicious code can execute. All right, now the most common way of executing malicious code is to place the code in memory itself. Okay, now we have said that we are jumping into certain location. Now, and that location, that malicious code has to be there. But how does code go there? Okay, you have to think that how we are going to place the malicious code also. Right now, we have manipulate only jumping address of malicious code. Okay, so there is something called shell code. Okay, it's a malicious code inserted by the attacker into memory to be executed using memory safety exploit. Okay, it's called shell code because it usually spawns a shell or terminal. So we'll look at how and can of course do all malicious things like deleting a file, and it can encrypt and do a lot of other things. Okay, of course, yeah, I mean, whatever shell normally can do. Okay, so all right. So now attack is as follows: find the memory safety vulnerability. That's the first thing that attacker has to find out. Is there a vulnerability of this kind? Okay, and for that, attacker may experiment for months together and so on, or use some tools which will generate certain sequence and of input and try to crash the system and so on. And it's like a role of a doctor, right? Looking at patient has to find out there's something is wrong. Is there something wrong or not? Similarly here, attacker has to find out is there something wrong. So first thing is going to find out memory safety vulnerability, like buffer overflow. Okay, and then write malicious shellcode and known memory address. Fine. How? That you can find out. Okay, do little bit of googling. So we'll tell you one way. Okay, override the rib with the address of shellcode. Okay, return then return from the function. Then obviously return goes to malicious shellcode. That's it, right? So let's look at this example. So this is the code. So shellcode is, let's assume, so this is the code which is correspondingly stack is here. And then shellcode is say 12 bytes long. Okay. And assume that the address of the name is, okay, the address starts from here. Okay. So now what should be the input? Okay, so let's look at this one, right? Okay, so now you put shellcode here. So instead of putting all A, since it's a 12 bytes, so put shellcode here. And now, this RIP, you should give address of where this shellcode is starting. Okay, now so when this program gets over and you give this intelligent input of all these A's and return address, and when this gets over, new old PC is loaded, and then old PC is nothing but this point, and then shellcode. As a result of that, next instruction to be executed corresponds to first section of shellcode. Okay, so this should be your input. All right. Okay, so alternative is that you can put shellcode here. Okay, and then accordingly you'll have to give the input. So it should be 12 times A, which is here, then shellcode, and then return address. Okay, now the question that comes, so here after it returns, it will come here because return PC will point to this instruction. What the question comes to your mind? If shellcode is more than 12 bytes, then what to do? Then you can put shellcode here, anywhere in the stack. Okay, so you can put shellcode here and put intelligently all these characters, and then put return address as a beginning of where shellcode starts, this one. All right. Okay. Any question? No? Please go to PPT, you will understand it, right? Okay. So this you can walk through this, because now what we have been doing is we are looking at only in terms of C code, right? C code is not known to attacker, right? So let's assume that how does it run from corresponding machine instruction. Now, of course, there's assembly here, right? Same thing you can see here. This name string of 20, then get name, and so on, right? So you can see that shell code is 12 times A and some address. So we can see the shell code will come here, and then A. So first shell code and then A. Okay. So now 12 A's will come. So this A's will get overwritten over. Okay, just a minute. Okay, so A also gets written over starting frame address. So now that is also becoming corrupted. Now once you write something here, it will point to some area, something, some junk. Okay, so anyway, the program execution is will get disturbed, and then rip of vulnerable, you'll have to write to which was pointing to next instruction in the code. Now it will point to this one, beginning of shell code. Okay, and accordingly, your stack pointer etc. will change. All right. So here is shown as how stack pointer and EIP will change when this execution happens. Where you can see in the red where the current instruction is being executed, right? Okay, so you will see that how different both stack pointer and base pointer will change, right? And we have studied this in detail in the last class. So you can now make out. All right, another 2 minutes and we'll close. All right, so you go through this, is quite simple. You can see that, let me just okay, when instruction, just a minute, after this, when this is executed, then it will start filling shell code, because input is this one. Okay, and as a result of get, again the 12 times A will be written here. So now we can see that SPF gets screwed up. Okay, and then we write appropriate value of RIP, a return instruction pointer or old PC, which will now should point to this starting address of shell code, the one here, right? Okay, shown here. All right, and when when this execution is over, it comes to return. Return means that now you load the old program counter, and then as a result of that, yeah, so it's okay. As a result of that, this RIP, okay, sorry, this return instruction pointer will point to the beginning of the shell code. So that's it. All right. Okay, and when this executes, then if the shell code is appropriate, then we'll get shell, and then you can exploit things. Okay, any question?
Sir, I have a question.
Yeah.
Yeah, so everything in the stack frame, it is like initialized in runtime, like it is assigned. And how will the hacker know that he have to place this address? Like, can you go to the previous slide once?
Yeah.
Yeah, so here, like, we know that there are these many bytes after shellcode, which we need to fill with A, and then we know the address of what address we have to fill. We have to basically fill the shellcode address. But everything is happening at runtime. Then how will the hacker know that this much amount of space is left and he have to overwrite here this address and all that?
So that see, lot of stack designs are known. Okay, so it's not that totally unknown things, right? I mean, for Intel and other processor is kind of published, is known. And then there are, of course, there are, when a stack is created, then it has to reserve some areas, right? Okay, but all this is based on experimentation. It's not that, once you know that this, you as a hacker know there is a vulnerability, you can just write something and then it works, right? So it's based on experimentation. Basically, how do you know this is a starting address?
And even that address changes after every execution. Like one time when we execute, the address might change
Yeah, so
for the next time.
yeah, but yeah, so all these things have to be see, all these are relative address somewhere or other, right?
Yes, sir.
Okay, I mean, the way stack is actually filled is also relative to base pointer somewhere, right? So all these things are, hacker will of course know what is size of shellcode, okay, and it will know relative position where it has placed the shellcode. Okay, based on that is all experiment he or she has to do to find out what is the address, right? Yeah, you are right. So it does not come by just looking at it and so on. That's the reason hacking is not that simple. Okay, so this value, you can write junk, that's very simple, but accurate value is comes through some wild guesses and then some previous experience and so on and so forth, right? And some other information that you have about where exactly in relationship to this written RIP, where should it be, and so on. It may require 100, maybe 1,000 attempts and so on. Okay.
Yes,
All
sir.
right. You can experiment this. Actually, we'll give an exercise and then try experimenting with it. Okay. All right. Okay, so that's it for today. So we have vulnerable C library function gets, and there is solution for that. There can be, you can use fgets. Instead of string copy, you can get str and cpy. Instead of strlen, you can use strnlen. Okay, so all these are better programming features to use. All right, so self-read. So what we studied only about the stack vulnerability. Now you can read about heap vulnerability. You can also play with the printf character, right? Printf, see what is syntax, can you play with it? And there are some vulnerabilities, right, which have been exploited. All right, so just start thinking about it and we'll give you one assignment. Okay, and then you can experiment. Of course, I will request all of you to have virtual machine. Okay, so create a VM and then on VM I'll send you instructions what is to be done. Okay, but on your machine you will do this, and you will have to load some version of Ubuntu and some disable some things like something called address space randomizer, which now machines use, where address space can be randomized. Now the guessing where to jump becomes very hard. Okay, and there are some other mechanism we'll study little later. Okay, but start thinking about it and start thinking as a hacker, ethical hacker. All right. Okay.